Unit 6 review problem number 3. In this particular problem, we're told that we're working with an imaginary quantum mechanical atom and that we're supposed to focus on the 1s, the 2s, the 2p, and the 3p sublevels. We're given some wavelengths that belong on our spectrum, as well as the energy differences between a couple of our different sublevels. Before we get started, let's consider some of the things that we know. These are our equations that are going to move us between wavelength and energy. These are going to be provided for you on your test, along with the appropriate physical constants. It is important to notice that the speed of light is given in meters per second, so if we want to work with wavelength in this equation right here, because the speed of light is part of that equation, our wavelength is going to need to be in meters. Notice that my wavelengths here are given in nanometers, but I'm also provided a conversion in order to get to meters. Also notice that your link to energy is to come through frequency, so you're going to have to go from wavelength to frequency to energy if you need to get from wavelength to energy, and if you need to get from energy to wavelength, you're going to have to go from energy to frequency and then calculate your wavelength. I also think we should probably put some information on to this diagram down here. We're given the energy difference between the 2p and the 3s, as well as the energy difference between the 1s and the 2s. The first part of this is going to be to find our missing stripe. In order to do that, I'm going to assume that one of these two energies is going to be associated with our missing stripe. I'm just going to try to guess and check here. If you start with the one up here, 2.12 times 10 to the negative 18th joules, go from energy to frequency, frequency to wavelength, and put that into nanometers, you should come up with 93.8 nanometers. That's already on the spectrum, so that's not the one we're looking for. If you try the other one, the 4.87 times 10 to the negative 18th, use your equations and convert to nanometers, you get a wavelength of 40.8 nanometers, and that one's not on our list, and so that must be our missing stripe. The next part of this we can tackle in one of two different ways, and I'll show you both methods for doing this. Both methods do require you to think a little bit in terms of the meaning of the different wavelengths on your spectrum. We know that the largest wavelength is going to be associated with the electron falling the smallest distance. If you look at our energy spacing here, the smallest energy difference is between 2p and 2s. Knowing that that's the smallest, we will realize that when an electron falls from the 2p sublevel to the 2s sublevel, it will emit a photon of light with a wavelength of 552 nanometers. The other thing we know is that the biggest energy gap is going to be the gap between the 3s and the 1s sublevel. As an electron makes this huge energy drop from 3s down to 1s, large energy is associated with very small wavelength. It's going to give off a photon with a wavelength of 27.0 nanometers. So, to find the missing piece of energy, the easiest way to do this is just to use the smallest energy stripe, 552 nanometers. If I take 552 nanometers, convert that to frequency, and turn it into energy, I get that the energy gap between the 2p and the 2s is 3.60 times 10 to the negative 19th joules. And that's a perfectly legitimate way to do this. The other possibility is to use subtraction. Now, wavelengths don't add and subtract very well, but energies add and subtract very well. The other possibility is to calculate the energy difference between the 3s and the 1s, and then subtract this piece, subtract that piece, and leave you with this piece in the middle. And that's the last part of this. Method 2 would be to use the largest energy stripe, find the 3s to 1s transition, and then do some subtraction. The largest energy gap is associated with the smallest wavelength, so that's the 27.0 nanometers. That's equivalent to 7.35 times 10 to the negative 18th joules of energy. So now if I want to get that little tiny gap, I'm going to take the big gap, subtract two of the pieces, and I'll end up being left with the energy of the littlest piece, which is the gap between the 2p and the 2s. In this particular method, we end up with one less significant figure, just because of the rules of adding and subtracting having to be applied here. These are to the negative 18th. My answer is times 10 to the negative 19th. But both methods are equally good. If you're going to use adding and subtracting methods to find energies, just remember that you have to add and subtract while you have energy, and then convert to wavelength when you're done. Energies are additive and subtractive. Wavelengths are not additive and subtractive.